let's quickly review power series and radius and interval of convergence. So a power series is a series of this form where c sub n are the coefficients. C sub n times x minus a to the nth is c naught plus c1 times x minus a to the first plus c2 x minus a squared, and so on and so forth. These series are what we say are centered at x equals a, and therefore will converge for certain values of x on what we say is an interval of convergence, which has a radius equal to r. So that's our definitions, and we have three distinct possibilities when we are centered at x equals a. So if we are centered at x equals a, let me actually grab my black pen here. If we are centered at x equals a, then we have these two extreme possibilities. It could be that we converge for just x equals a. The only value we converge for is when x equals a, which of course if we plugged in x equals a right here, we will always have convergence at least x equals a. Because if we plugged in x equals a, that would zero out the series. And so this is very limited, very restrictive. This is only converges at a single point x equals a. So there is no radius. The radius of convergence here, the distance we can move away from a and still have convergence, is actually equal to 0. Now, the other possibility, the other extreme possibility is that the radius is infinity. So from a, we converge for all values of x to both the right and to the left of a, giving us a radius of convergence. So we're going to converges for all values of x. So that gives us what we call is an interval of convergence of negative infinity to infinity. We can go in either direction in infinite distance and still have convergence. We converge for all x's. You could also say you converge on the set of real numbers. Now, if r is a finite positive number. So if r is a positive number r, and we converge when the distance, remember that when we say the absolute value of x minus a, that's the distance of x away from a is less than r, and diverge when that distance is greater than r, then we call r the radius of convergence, and the corresponding interval is the interval of convergence. Now, because of the possibility of convergence or divergence at the endpoints, when we are centered at a and we can go a distance of r in either direction, we can go to a minus r, a plus r. So if the radius of convergence is r, that means that we have convergence on the interior of this interval. What we don't know is if there is convergence at the two endpoints. So notice here that this interval of convergence could have four possibilities, where we do not include the endpoints, where we include both of the endpoints because we have convergence at both, or where we have convergence at just one of the endpoints. So in this scenario, we actually have to test the endpoints of what we call is the interval of convergence. I'll abbreviate IOC for convergence. So when we're testing a radius of convergence that is finite, we will also be testing the endpoints to see if we have convergence at those endpoints. Okay, let's look at a couple examples and talk about the process for finding this radius and interval of convergence. So this first example, so if we want to determine the radius of convergence and interval of convergence for this particular power series, we want to find the values of x for which this series will converge. So how are we going to do that? Well, before we just start jumping into the radius of convergence, let's just see, what does this power series look like? So when n is actually, so we start at 1, so when n is 1, what would be the first term in this power series? So when I plug in 1, I get a positive 1, negative 1 to the 0. In the denominator, I would get 1 factorial, because I plug in 1 for n, and then I'm going to have x minus pi over 3 to the first power. Now when n is equal to 2, the next term in this power series is going to have a negative 1, because when I plug in 2 there, I'd get negative 1 to the first. When I plug in 2 here, I'm going to get 4 minus 1, so 3 factorial. And notice that the factorial and the power are the same, so this will be x minus pi over 3 to the third. And because of that 2n minus 1, that's always going to be an odd number, so as we go up in the index, n equals 3, the next term in this power series would be positive 1 over 5 factorial. We've got that switch happening, so the signs are alternating. And the factorial and the power are corresponding and they are odd numbers going up. So plus, actually the next term would be a minus because of the alternating signs, minus dot dot dot. We would continue. Okay, so that's what this power series looks like. It is centered at where this x minus pi over 3 is equal to 0. So when x is equal to pi over 3. So let's determine where we're centered at. And let's give a little graph of that so we have a visual. So we've got this power series, which is an infinite polynomial, and it's being built around pi over 3. As we add the terms, we're getting an ever increasing polynomial, and it's centered right there at that x equals pi over 3. So that's where we're centered at. Now the question is, how far can I go in either direction and get convergence? So for what x's, the question that we're asking, for what x values does, that I could plug in for these x's, does this series converge? So that's the question that we're asking. So how do we figure that out? So let's take a look at some steps for doing that. So again, we're trying to find, I have a nice little picture here that we can use. We want to figure out what is this radius? How far away from that center point of our power series can we go to the left and the right and have convergence? Now the interval itself is going to be converging absolutely. At the endpoints, that's what we have to think about. Do we have convergence at those endpoints or not? And it could be conditional convergence at those endpoints. So we already did the first step, determine where we are centered. So that's the first thing we want to do. So we're going to determine where we're centered at. We figure out, okay, I like to use a little number line, think of it as my x number line, and think about where is it that I'm centered at? What is my center point? And then we're going to use one of our tests for convergence. Now, the test for convergence, the first one that I would suggest that you start with as we're trying to figure out the radius of convergence, because it gives us a nice inequality for where we will have convergence, and that is the ratio and the root test. So we'll start with the ratio or the root test. We'll run through, just as a reminder, the ratio or the root test as we take the limit as n is going to infinity of the a sub n plus 1 term over the a sub nth term. Take that limit, run it through, or the root test says define the limit as n goes to infinity. We could say n or we could say k, doesn't matter, of the absolute value of the a sub nth term to the nth, 1 over nth power. Take the nth root. Remember, 1 over n is the nth root. So those are good possibilities. So here's our ratio and root test. So good possibilities. If it turns out that the radius of convergence through that test, when we run that test, we can see if the radius is one of the extremes. If the radius of convergence is 0 or infinity, then we are actually done because we know that the radius is that one of those extremes, and it also gives us the interval of convergence. So remember, if the radius, just a quick note, if the radius of convergence is 0, then the interval of convergence is simply that single point. It's not actually an interval, it's just that point. If the radius of convergence is infinity, then the interval of convergence is the whole number line. So the interval of convergence is from negative infinity to infinity, or you could also state it's the real number line. Okay, if it turns out, on the other hand, that we actually have a value of r, a positive number r, if it turns out that our radius is some positive r, then we actually have to think about what's happening. We will know what the interval of convergence is. The interval of convergence will be from, let's go ahead and write it out. It'll be from a minus r to a plus r, because we start at r. If we get an r value, we will add r, and that will take us to a plus r, and we will subtract r, and that will take us to a minus r. So we will get that interval. We'll know the interior of the interval of convergence. We know we will have convergence, absolute convergence, from a minus r to a plus r. But then we have to actually test those endpoints. So then we test those endpoints because it could be that we have one of these 4 possibilities. So we test each of the endpoints. So we need to test x equals a minus r and x equals a plus r. So we will test each of the endpoints to determine if we can include them or not include them in our interval of convergence. Okay, So those are our possibilities. We've already started on our example. We've already determined where we're centered. So let's go ahead and head into the rest of the steps by applying the ratio or the root test to determine the radius of convergence. And then we'll follow it up by determining the interval of convergence. So here's my power series, and I'm going to go ahead and apply the ratio or the root test. In this case, because of the factorial, I'm going to go with the ratio. I'll write it out. Ratio test. Ratio test is super handy when we have factorials because of the way factorials, when we look at a ratio, will reduce and cancel. So let's go ahead and apply the ratio test to determine what our radius of convergence is. So let's take the limit. We've got an index of n, so it's going to be n going to infinity. Just a quick reminder on the ratio test is going to be the a sub n plus 1 term times 1 over the a sub nth term. I do like to write it that way because, of course, they're fractions, so that makes it easy. So let's take the limit as n is going to infinity. The n plus 1 term would be negative 1 to the n over it's going to be 2 times n plus 1 minus 1 factorial. Now that, when we plug in the n plus 1, becomes 2n plus 2 minus 1. So 2n plus 1 factorial in the denominator there. So we're going to get 2n plus 1 factorial in the denominator. And you know what I'm going to do, because I'm going to just move this guy up into the numerator. So this is going to be x minus pi over 3. That is also a 2n minus 1, so when I plug in n plus 1, I get 2n plus 1 on the power there for the n plus 1 term. Then I multiply by the reciprocal of the nth term, and the nth term is how the series is defined. So it's just going to be the reciprocal of how the series is defined. So in the bottom, I have negative 1 to the n minus 1 times x minus pi over 3 to the 2n minus 1. And in the bottom, I have a 2n minus 1 factorial. So when I reciprocate it, it goes to the top. Okay, so that is our ratio, and we need to take the limit. So I'm going to go ahead and simplify here, and my limit as n goes to infinity. As I'm simplifying, I'll go ahead and write it all out here for you guys on this first one. Negative 1 to the nth over negative 1 to the n minus 1. With ratio test, I like to group. I've got my factorials. I have 2n minus 1 factorial on the top and a 2n plus 1 factorial on the bottom. And then I've got an x minus pi over 3 to the 2n plus 1. And in the bottom, I have an x minus pi over 3 to the 2n minus 1. Now, lots of canceling. Quick note on this first one. When I do this, I end up with negative 1 to the first power in the top, but it's in absolute value. So that becomes a positive 1, and I'm not even going to write it. When I take that absolute value, that becomes a positive 1, so I'm not even going to write it. On this second one, when I have 2n minus 1 factorial. Now, I could write that out. That would be 2n minus 1 times 2n minus 2, all the way down to a 3 times 2 times 1. Now, on the bottom, when I have 2n plus 1 factorial, remember that that is 2n plus 1 times 2n minus 1, all the way down to 3, 2, 1. So just a quick reminder on factorials. When the factorials have a difference of 2, that means that the larger factorial has 2 additional factors. So that has 2n plus 1 times 2n, and then it's going to be times 2n minus 1 factorial. So when I get my canceling there, the 2n minus 1 factorials are going to cancel, leaving me with a 1 in the top, and then a 2n plus 1 and a 2n in the bottom. All right, now on this guy, when I do this canceling, we end up with an x minus pi over 3 to the second. When I subtract the powers, there's a difference of 2, and that difference, of course, is in the numerator. So we have x minus pi over 3 to the second power. Okay, so all of that's in red, my work for the simplifying. So I have the limit. So L is equal to the limit as n approaches infinity. The negative 1 became positive 1, so I don't even write that. In the factorial here, as I canceled here, all that was left was 1 and 2n plus 1. My work above and below was just to show where that was coming from, how I was rewriting it. And so we end up with, that's in absolute value, but the factorial is always positive. So I'm going to also drop the absolute value on that. That's 1 over 2n plus 1 times 2n. And we're multiplying that by, now I do need to leave the absolute value here because I don't know what x is. So this is the absolute value of x minus pi over 3, but I can move the square outside the absolute value, or I can move the absolute value inside the square. Okay, now this becomes the limit as n is approaching infinity of the absolute value of x minus pi over 3 squared divided by 4n squared plus 2n. Now, I went ahead and simplified a little further. I didn't really need to, though, because as I take that limit, as n approaches infinity, so as we're letting n grow without bound, what's going to happen is we're going to get x minus pi over 3 squared, an absolute value, divided by something that is growing without bound. So divided by infinity. So as n goes to infinity, that numerator is a constant in terms of the limit. So as n goes to infinity, this is going to zero out. So L is actually equal to, when I take that limit, this is equal to 0. Which, remember, we're running I know we've gone through a lot of work here to simplify, but we're running a ratio test. And so remember, in the ratio test, if L is less than 1, we have absolute convergence. That's what the ratio test tells us. Well, L equals 0. It is always equal to 0. So that means that that is always less than 1. This is always less than 1. Or always true. This limit is always going to be less than 1. So what that tells us is that we are converging for all values of x. We're going to converge for all values of x. This is always true. This gives me that extreme value. So what this tells me is that my radius of convergence is infinity. We're going to converge for all values of x. Remember, that was the goal. That's what we're trying to find here. Let's go back to where we were at. We were trying to figure out for what values of x, right? This is our x. We're centered at x equals pi over 3, and we're trying to figure out how far away from pi over 3 can I go and still have convergence. Well, we just showed that for all values of x, we get convergence. So what that means is that we can go all the way on either side of this number line. We can go to either end of that number line going to infinity. Our radius is actually infinity. So we can go both directions. You know, the radius is infinity, so we can go to the right and to the left, and we get an interval of convergence that is the whole number line. So our radius is infinity, and our interval of convergence, and I will abbreviate IOC, is going to be from negative infinity to infinity. So this is one of the extremes. It turned out that when we ran the ratio test, we found that it was always convergent because we were always less than 1. And if we're always less than 1, then our radius has to be infinity. Okay, let's look at another one. Let's take a look at this guy. So if we're running a power series that looks like this, k equals 0 to infinity of 5 times x to the k. Let's see first what that looks like. And because it's 5 times x to the k, let's rewrite it just a little bit. This is 5 to the k times x to the k so that we can see where we're centered at. So we are centered at, this is like an x minus 0 to the k. We could also just set x to the k equal to 0, but we are centered, start there, centered at x equals 0. So we are centered at x equals 0, and the goal here is going to be to figure out how far can we go in either direction and still have convergence. So let's write out a couple of terms in this power series. So when x equals 0, we get 1. And no alternating sign, so the next term is going to be 5 times x, and then the next term is going to be 25 times x squared, and 125 times x cubed, and so on and so forth. So what values of x can I plug in here? So what values of x could I plug in and still get convergence? That's what we want to know. So what values of x could I plug in and get convergence on this infinite series? And again, our process for doing this, the first thing we want to do is we want to run a ratio or a root test. So that's where I'm going to think about which of those should I use? Well, I've got this whole thing is raised to the kth power. We could look at this term here. And so this is looking like root test would be a really good possibility here. So remember, for the root test, I'll just rewrite it. It's the limit. We've got an index of k, so we're going to let k run to infinity. We're going to take the kth root of the a sub kth term. Now, when we do that, that's the same as taking the absolute. Oh, we should take the absolute value. This it turns out this guy was always positive, but we do want to take the absolute value. Absolute value of the kth term raised to the 1 over kth power when we take the kth root. So that's what we're going to do. We're going to run that root test and see what we get a result for our radius of convergence. So we're going to take the limit as k, we're going to define L to be the limit as k approaches infinity. Again, I mentioned a second ago, but these terms are all positive. But when we take the absolute value, it's not actually necessary in this case for k greater than 0. But we'll go ahead and do it. So to the 1 over kth power, so what ends up happening there? Well, that becomes the limit as k approaches infinity. We end up with 5, when we take the 1 over k term, times the absolute value of x to the, now when we plug in, or when we take the kth root, it becomes k over k, which is to the first power. So that's to the first power. 5 was to the first power as well. I mentioned earlier that these terms were always positive. I was thinking about the 5, but x could be negative. So we do definitely need that absolute value. We want to make sure we keep our absolute value there. Okay, so this is the limit as k is approaching infinity, but k is no longer there. So this limit is a constant in terms of k. So this limit is actually just equal to 5 times the absolute value of x. So our limit through the root test is just 5 times the absolute value of x. But we know that that will converge. This converges. By the way, it converges absolutely. I'm saying convergent, but it converges absolutely when this limit is less than 1. So that's why the root and the ratio tests are so powerful, because we're able to make that conclusion. We can take the limit and we can say, okay, this is going to be convergent when 5 times the absolute value of x is less than 1. But again, remember, we're trying to figure out how far away from 0, so we need to isolate. So now let's isolate the absolute value of x. What we want to do is we want to isolate the absolute value of x minus a. In our case, that's just x minus 0. Let's go ahead and write it, x minus 0 in absolute value. So we want to isolate that absolute value of x. That will tell us what the radius of convergence is. So the absolute value of x, if we take 5 times the absolute value of x, has to be less than 1. Well, that means that the absolute value of x must be less than 1/5. That means that the distance of x away from 0 can be at most 1/5 to give us convergence. So from 0, that's telling me right there, that's giving me my radius of convergence. My radius of convergence is 1/5. So from 0, we can go 1/5 to the right, and we can go 1/5 to the left. So from 0, that takes me over here. I'm going to make it dramatic here, even though 1/5 is kind of small. That takes me over here to 1/5 and over here to minus 1/5. So we know that we converge between negative 1/5 and 1/5. What we don't know is what's happening at 1/5 and negative 1/5. Should I put a parenthesis or should I put a bracket? That's what we don't know yet. So we've got to get in there. We got to figure out, we got to test those endpoints. But we do know that the radius of convergence is 1/5. So now let's figure out the interval of convergence. So the interval of convergence, I zoomed out so that we could see my little graph there. My interval of convergence, I'm going to carry the graph down here. My interval of convergence, the possibility, actually I put a parenthesis, but we don't know that yet. My interval of convergence, the potential interval of convergence between negative 1/5 and 1/5. So what we need to do is we need to test those endpoints. So it keeps, when I squiggle, it keeps getting rid of my drawing. So we know our interval of convergence right now, we know is between negative 1/5 and 1/5. What we need to decide is what we're going to put at those endpoints of that interval. Do we include those or do we not? So let's test the endpoints. So the endpoints, we've got two of them. We've got x equals minus 1/5. So let's plug that into our series. Our series has zoomed way up above. So we're going to plug that into our series. So when I plug it in, I get 5 times a negative 1/5 to the k. Well, what that becomes is negative 1 to the k. Now, k was starting at 0. It actually wouldn't really matter. K starts at 0 to infinity. As we run out negative, this becomes the sum of 1 minus 1, 1 minus 1. We're adding and subtracting, adding and subtracting. We can see actually that this is going to diverge because the limit as k approaches infinity of negative 1 to the k doesn't exist and is not equal to 0. So this diverges by the divergence test. So we know that we cannot include, right? We can't include negative 1/5. So when I come back to my interval of convergence, I have to put a parenthesis. I cannot include negative 1/5. Okay, so we tested negative 1/5. Now we got to test 1/5. So let's test x equals 1/5. When we test x equals 1/5, when we plug that in from k equals 0 to infinity, I get 5 times 1/5 all to the k power. So that becomes, well, that just becomes 1 to the k as k equals 0 to infinity. Of course, that's just the sum of 1. So it's 1 plus 1 plus 1 from k equals 0 to infinity. Well, same thing that we just talked about, that is also going to diverge by the divergence test. So we can say that this guy diverges because the limit as k goes to infinity, that limit actually exists. That's equal to 1, but that's clearly not 0. So that guy diverges by the divergence test as well. So my interval of convergence cannot include either of the two endpoints. So on this series that we're looking at, this series has a radius of convergence. So it's centered at 0. It has a radius of convergence. Let's come back to my graph right here. It has a radius of convergence of 1/5 and an interval of convergence of negative 1/5 to positive 1/5. So we would say here that this has a radius that is equal to 1/5 and an interval of convergence that is between negative 1/5 and 1/5 because we are centered at 0 and we can go to the left and the right 1/5, and we showed that each of the endpoints themselves had divergence, therefore we couldn't include them in that interval of convergence. Okay, let's end this video with just one more example. Okay, so here we've got the series from n equals 1 to infinity of n factorial times x plus 5 to the n minus 1. So first things first, let's figure out where are we centered at. So we are centered at, in this case, x, when does x plus 5 equal 0? So that's when x equals negative 5. So we are centered at negative 5. And we need to figure out how far can we go from negative 5 and still have convergence in this series. So what does this series look like? Let's just write out a couple of terms. When n equals 1, we'd have 1 factorial times x plus 5 to the 0. So we'd have 1 factorial plus, and then when n equals 2, we'd have 2 factorial times x plus 5 to the first power. And then we have plus on the next term, we'd have 3 factorial times x plus 5 squared plus 4 factorial times x plus 5 cubed, and so on and so forth. So for what values of x around x equals negative 5 will we have convergence? So for what values, that's always what we're thinking about when we're thinking about the radius and interval of convergence. So for what x's will this series converge? All right, so that's the question. So we want to think about, to do that, what we're going to think first about is, do we want to use a ratio or a root test to get us started? And so when we're thinking about the ratio or the root test, always kind of think about if you've got a Factorial, think about ratios because ratios are nice with factorials. You get nice little canceling. So we're going to run that ratio test, the limit as n approaches infinity. Quick reminder, that's n plus 1, 1 over a sub n. So we're looking at the ratio of a sub n plus 1 over a sub n. Oftentimes it is easiest to write that as a sub n plus 1 over 1 plus the reciprocal 1 over a sub n. So we're taking the limit as n approaches infinity. We're going to get n plus 1 factorial times x plus 5 to the, when we plug in n plus 1, we get to the nth power times 1 over. Now this is one case because it's not actually a fraction. This is one case where we could have just written that as n plus 1 over a sub n. We're so used to writing it that way. And I didn't even look at it when I rewrote it. So we can just write the nth term on the bottom, n factorial over x plus 5 to the n minus 1. Now let's simplify that down. And that becomes that limit as n is going to approach infinity. We're going to let n grow without bound. Now, quickly on these factorials, remember that n plus 1 factorial is just n plus 1 times n factorial. So the n factorials would cancel. So we end up with the absolute value of n plus 1. And we end up with, on the top, we end up with x, just one factor of x plus 5 to the first factor, to the first power. Now the n plus 1 is always positive, so we could just put the absolute value around the x plus 5. And we're going to let n go to infinity. So as n goes to infinity, remember the x plus 5 in absolute value is a constant in terms of the limit, and n is going to grow without bound. So this is going to become infinity times a constant, so infinity. So this is going to approach infinity. This limit is approaching infinity, which this is another one of those extremes. When this limit comes out as infinity or 0, you have to think about what that's telling you. This is infinity, and remember that on the ratio test, let me go to my red, remember that the ratio test says that if L is less than 1, you have convergence, but if L is greater than 1, even infinite, greater than 1, it is divergent. So the ratio test, that's what the ratio test tells us. So infinity is always, always, always greater than 1. This is always divergent. So if this is always divergent, so this series is divergent for all values of x, except for that one value where it is defined. Because of course, if we were to plug in -5, this series becomes 0, and it does converge at 0. But this series is always divergent. It diverges for all values of x, except for that one. So what this means is that the radius of convergence is 0, and the interval, it's not really an interval of convergence, but the interval of convergence is simply that one point at 5. If we were to think about what this looks like graphically at -5, we have convergence only at 5. That's the only spot. We can't shade anything else in. It's only convergent when x equals -5. And so, again, you have to think about what the result is that comes out. If it's one of our extremes, if that result is 0 or infinity, we have to think about what that means in terms of the ratio test. And so if that limit comes out and is infinite, that means that we are always divergent because that is always greater than 1. All right, so that is the final example for this video. I know this video ran a little bit long, but I wanted to get through 3 different examples on power series here so you could see the 2 extremes plus testing the endpoints. So just practice with these, run your ratio or your root test, and if you have a finite value, then also check those endpoints for convergence or divergence.